Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I am the director of the Planetarium, and it's just me tonight. So, what we're going to be doing tonight is going on an adventure through the universe, which is going to be a lot of fun. There's a lot to see and not a lot of time to get to it, so we're going to do as much as we can in the roughly 30 minutes that we have for these shows. So, as always, if you have any questions throughout the show tonight, feel free to leave them down in the comments. Since I am alone, I am going to be trying to do all of this juggling, running the program and talking with you guys and answering questions. So if I'm a little bit slow to get to questions, just be patient with me. I will make sure that I take time at the end to answer any questions that I missed. The other thing, since our solar system is a part of the universe, we're going to start off going to a few planets, but we don't have time to go to all of them, and we also have a whole other show that does specifically a tour of the planets of our solar system. So I want to hear from you guys. Which planets do you want to see? Let me know in the comments. All right. Well, I'm going to get us switched over here. And for our tour of the universe tonight, we are using a program called OpenSpace, which basically takes all of the data for locations and positions of planets and stars and galaxies and things in our galaxy, and it creates a 3D model of them so that we can actually travel to and fly through the universe and visit all of these things. It's pretty similar to, if you've been to our planetarium, the program we use in the planetarium itself. Not quite as advanced as that, but still a really great tool, especially for doing online shows like this. So as I said, since we are located on Earth here in the solar system, that is the kind of beginning of our universe. And Earth is only one of 8 planets within our solar system. We're going to start off going to a few of those planets. And I'm not seeing any particular planets that anyone would like to go see. So I did end up asking my mom earlier today because she said she was going to be at the show, and so she made some requests. So I'll go with those. So we're going to start with the closest planet to the sun. We're going to go visit Mercury. So we're going to fly on in now to Mercury. And a lot of people's first impressions is, wait, no, that's the moon. And I mean, yeah, there's a good reason for that. Mercury does look a lot like our moon. They are very similar objects. They're both these big spheres of rock that are grayish in color and covered in craters. Mercury is a little bit bigger than our moon. So the moon is about a fourth the size of the Earth. Mercury is about a third the size of the Earth. So it's still pretty small, but a little bit bigger than our moon. And we see a surface covered in all of these craters because Mercury doesn't have any processes that erase those features after they form. So if you think of like here on Earth, we have erosion that grinds things down. We have volcanoes that paves things over. Plate tectonics that destroys and recycles the crust of the Earth. Mercury doesn't have any of that. So when a crater forms, it basically just stays there forever unless something else hits right on top of it, and then the crater might get destroyed, but that's because a new crater has formed from something new hitting. And so that's how we end up with so many craters on this world. Now, since it is the closest planet, it of course gets very hot. Daytime temperatures can get over 700 degrees Fahrenheit, but at night they drop down to about negative 200, and that big temperature swing can actually have an effect on the rocks on the surface. It kind of degrades the integrity of the rock, and we find that they kind of break a lot easier because they're so strained from that constant extreme temperature change from really hot to really cold. Okay, well, since we visited a planet in the inner solar system, let's go visit a planet in the outer solar system. And let's see, I'm going to pick, I feel like Jupiter and Saturn always get picked, so let's go with Neptune. Which is good. We'll do the closest planet to the sun and the furthest planet from the sun. So Neptune sits about 40 times further from the sun than Earth is. It is quite a bit bigger than Earth. Its radius, its diameter, is about 10 times that of Earth. And it's this beautiful blue color. That blue color actually comes from methane in the clouds. Methane is really good at absorbing red light, and it reflects blue light. And so it's the blue light that bounces off the clouds and makes it back to our eyes. And even though the methane is giving the clouds the color, it's actually not what the clouds are mostly made of. The clouds are mostly made of hydrogen and helium, just like Jupiter, Saturn, and Uranus. There's just enough methane in the clouds to color it and give it that blue color. We can also see some kind of whitish clouds, and these tend to be very, very high altitude clouds sitting at the very tip top of the atmosphere, and these are actually clouds of methane ice. And since it's not a gas, it doesn't interact with color the same way. So the solid methane doesn't interact with light the same way that methane gas does, and that's why it's white instead of blue. All right, let me check to see. All right, so in addition to the 8 planets and our sun, our star, that makes up our solar system, there is a lot of other stuff in here too. And a few weeks ago, we talked about some of the debris that's in our solar system. So we talked about the asteroid belt, the Kuiper belt, the Oort cloud. But another thing that we have in our solar system are what we call dwarf planets. And you probably know the kind of most famous of those, which is Pluto, which was another request from my mom to go see tonight because she knows I love talking about it. So Pluto was discovered after Uranus and Neptune in, I believe, the 1920s. Don't quote me on that, though. I'm forgetting the exact date. And when it was discovered, it was the only thing that we knew of that was out here past Neptune. So we called it a planet. Well, in the early 2000s, we started finding lots of other things out here in this same region as Pluto out past Neptune in a region we now call the Kuiper belt. And since we started finding lots of other things like Pluto, astronomers had to make a decision. Are all of these things going to be called planets? Or do we come up with a new category for the things that are like Pluto? And that's what they opted to do. And they called that category the dwarf planet. So Pluto is one of 5 confirmed dwarf planets. So in addition to Pluto, there is Aries, Haumea, Makemake, and Ceres. And there are about 10 other candidate dwarf planets. What we're really waiting to see is their overall shape, because one of the criteria to be a dwarf planet rather than like an asteroid or a Kuiper belt object or a comet is that they are big enough to be spherical in shape. And so those candidates were waiting to see their shape to see if they do meet that criteria and therefore can be called a dwarf planet rather than a Kuiper belt object. So this is Pluto. which is the king of the dwarf planets, the largest of all of them. And since we are really far away from the sun, Pluto is mostly made of ice. There is quite a bit of water ice, and at these temperatures, water ice is like rock hard. So a lot of these mountains that we see are actually mountains of water ice. But then we also have this kind of smooth region, which is kind of like a nitrogen ice glacier. And we're saying it's a glacier because we actually do see evidence of it slowly moving, the same way we see glaciers here on Earth moving. Overall, though, there is a lot that has piqued our curiosity because Pluto, these pictures that we got back from the New Horizons mission back in 2015, showed us a world that we did not expect. There are a lot of things here that we did not expect to see, especially like these really smooth surfaces. Remember, we said Mercury doesn't have a smooth surface because it doesn't have the processes to erase them, and we figured Pluto wouldn't either, so we expected to see, like Mercury, a surface covered in craters. And that's not what we see, which tells us that this has to be a geologically active world. But it's smaller than our moon, which is not usually an object that is geologically active when you get that small, at least not at this point, 4.5 billion years after the solar system has formed. So there's still a lot that we're trying to figure out and understand. And I should stop talking about Pluto, and maybe that will be next up in our exploration series. Maybe I'll just finally do an entire show about Pluto. Let me know if you like that idea in the comments. All right, so let's move away from our solar system. Because our star, the sun, and our solar system is, of course, one of many, many, many other stars out there in the universe. And a lot of these stars we have found do actually have planets around them. So I'm going to turn on, where's it at? Right there. What we're seeing here, every star that is circled with a blue circle is a star that we have found planets around. From our estimates, at least half of all stars in our galaxy have planets. And as our techniques get better and better, we are finding more and more planets that are like the Earth. And we estimate that probably about 20% of the stars in our galaxy have an Earth-like planet, meaning the same size and same temperature as Earth. And with, a couple 100 billion stars in our galaxy, that's an awful lot of Earths out there. Now, in addition to planets and stars, there are other objects in our galaxy. One of these types of objects are what we call star clusters, or kind of groups of stars, because stars often live in kind of groups together because stars are all born from giant gas clouds and multiple stars form at the same time. And so a lot of stars kind of end up spending their lives kind of hanging out with the stars that they formed with. And so star clusters come in a couple of different types. We have open star clusters. And so all of the green is locations of open star clusters. Let's see, we just got a question. Do you think there is life on any of these planets? Yes, I do. Purely from statistics. Hundreds of billions of stars, about 20% of those have Earth-like planets, and trillions of other galaxies out there with hundreds of billions of stars and planets of their own. Statistics just say, yeah, there's got to be other life out there. I am excited to hopefully have that confirmed and found in my lifetime. But yes, I do think there has to be other life out there. The universe is just far too big for there not to be. All right, so open clusters. The most famous open cluster that you probably have heard of is the Pleiades cluster. This you can see up in the winter sky. It's located in the constellation of Taurus the Bull. And so you can see open clusters are kind of smaller groupings of stars. We're thinking like thousands of stars. And they're kind of loosely grouped together. So they're spread a bit more apart, they're more irregular in shape. And oftentimes they represent very young stars because these are so, so loosely held together that passing stars can easily disrupt that and pull the stars away from each other. So these open clusters that we see tend to only have young stars because they tend to be dispersed pretty easily. All right, the other type of star cluster that we have is a globular cluster. And so now the yellow is showing us globular clusters within our galaxy. And a globular cluster looks like this. This is M13, or the Great Globular Cluster in Hercules. If you joined us for any of our star parties during the Dark Sky Caravan last week, you may have gotten a chance to see this one through the telescope because it is up in the summer sky, and it's a great one to look at. But you can see very different from the Pleiades, from the open cluster. First, we have a lot more stars. We're talking hundreds of thousands of stars. They're much more tightly packed together, and they have more of a kind of spherical overall shape to them. They're big globs of stars, hence globular cluster. These also tend to be very, very old populations of stars. We're talking some of the oldest stars in our galaxy live in globular clusters. And we think that's actually due to how galaxies form as a whole. Galaxies, we think, started off as smaller groups of stars, like globular clusters or dwarf galaxies, that merged together to slowly build up into bigger and bigger objects, forming the giant galaxies that we see today. So these would have been kind of those first populations of stars that formed and then kind of started merging together to build up the large galaxies that we see. And so that's one of the reasons we're really interested in studying these, because they help us understand that process and kind of get a sense for what the early universe was like, what stars were like back then, but also kind of build the picture of how galaxies formed. All right, in addition to stars, you can see really well that our Milky Way galaxy is also full of clouds of gas and dust. These gas and dust clouds are called nebula, or nebulae for plural. And the nebula come in a couple of different types. The first type are H2 regions, or star-forming regions. And you can see those are really concentrated there in the disk of the Milky Way, where you can see all of that gas really, really packed together there. And that's because these star-forming regions are exactly that. They're giant gas clouds that form stars. One that you can see in the winter sky is the Orion Nebula. And so these are kind of the largest of the nebulae, of the gas clouds, because you're forming hundreds and thousands of stars out of this gas cloud. And so they're kind of like our stellar nurseries. And so by studying these, they help us better understand the conditions needed to form stars and what young stars look like. The other type of nebulae that we have in our galaxy are associated with the deaths of stars. So first off, we have things called planetary nebula. And where are you at? There you are. The Ring Nebula here is a great example of that. This is another one that we looked at last week during our star parties in the Dark Sky Caravan. And so this is what happens to smaller stars, stars more like our sun. They gradually kind of just puff up and lose hold of their outer layers, and those outer layers just kind of blow away. And you end up with this kind of hot gas surrounding the dead star. And while they are still hot, they can glow, and we see that as this glowing planetary nebula. Then for the most massive stars, they have a much more chaotic death, where they actually explode in a supernova, and then they leave behind a supernova remnant, which I'm trying to, there we go. And the Crab Nebula here is an example of a supernova remnant. You can see much more chaotic, but it's still the same idea that it's all of the hot gas expelled from the supernova event, that while it's still hot, it glows, and we see this glowing gas cloud. What's really cool about the Crab Nebula, though, is we are fairly certain that Chinese astronomers actually saw the supernova that took place, that created the Crab Nebula back in 1050 to 1054. There we go. We see in their records that they saw this like guest star in the sky that faded away after a couple weeks. And when we look at the location of where that is in the sky, that matches with the location of the Crab Nebula. So we think that was them actually seeing that supernova, which is just really cool. All right. So let's keep zooming out here through our galaxy until we can see our galaxy as a whole. Zoom out a little bit more. So you can see that our galaxy is shaped like a disk with these spiral arms, so it's a spiral disk galaxy. Most of the star-forming regions are concentrated within those spiral arms. And so that's where we find the really young star systems, so things like those open clusters that we talked about. We also see a lot of supernova remnants because those form from really, really massive stars, which die very quickly after, and so they end up kind of going supernova in roughly the same region where they were born. And so that's within those same areas where we have those star-forming regions. The center of our galaxy is shaped it's a little elongated, and it's kind of hard to see in this model, but that is what we call a central bar. And at the very center of our galaxy sits a supermassive black hole. All right, so zooming out, our galaxy, and let me actually make this a little bit easier to see. So let's turn you guys off for right now and turn this on. Okay, our galaxy is part of what we call the local group of galaxies, which is about 60 to 70 galaxies that are grouped together. Most of these in the local group are small dwarf galaxies, but there are a couple of larger galaxies. The Milky Way is actually the second largest, with the largest galaxy being the Andromeda galaxy. And then the third is Triangulum. So let me, trying to find Andromeda. Where are you at? Over there. There we go. Andromeda is over that way. All right. So if we keep going out, and I turn the other ones back on, we see that our local group of galaxies is just one of many groups of galaxies out there. So now all of the dots that we're seeing are other galaxies that exist in our universe. And as we keep going out, we see even more and more and more. Now you notice that there are kind of two areas. Let me orient this a little bit better. Kind of top and bottom where we don't see any galaxies. That's not because there aren't any galaxies there. That's because looking in that direction, we have to look through our Milky Way galaxy, which, as we've seen, is full of stars and gas and dust, and that blocks our view of what lies behind it. So we just can't see what's in those areas, although we expect that it's filled very similarly to how we see everywhere else in the universe. And then as we keep going, we make it to the edge of our observable universe. Now, this doesn't necessarily mean the actual edge of the universe. See, funny thing is, light takes time to travel. And that's something we don't think about a lot because for us here on Earth, the short distances that light travels for us, it seems to be pretty instantaneous. But light does actually travel at a finite speed. It takes time. So it takes time for light from distant stars to actually reach us. And since the universe is a finite age, about 14 billion years old, light has only had that amount of time to travel to reach our eyes, or telescopes, since we don't really see these things with our eyes. They're too far away, too faint. So that means as far away as we can see is about 14 billion light years. There could easily be more out there. The universe is just not old enough for that light to have had time to reach us. So theoretically, the longer we wait, the more time we have for more light to reach us, and the bigger our observable universe gets and the more that we see. So what we're seeing the edge here is just the edge of what we can currently see today, but that is growing every second. All right, well, let's fly back home, back through the galaxies. Into our local group, into our Milky Way, through the stars, back to our home star, and back in to where the Earth is. So that has been our very quick tour of the universe. As you can imagine, there is a lot out there, and we've really just kind of scratched the surface there. But I hope you enjoyed that and kind of got to see what all is out there. All right. So if you have any other questions for me, go ahead and leave it in a comment. And I will give this a minute or so, because I know there's a little bit of a delay between me saying this and you hearing it. So while I wait to see if there are any other questions coming in, let me tell you about what's coming up over the next week. So on Saturday, we have another edition of Ask an Astronomer. So we will be here to answer your questions, whatever ones you have about anything astronomy related, or honestly, even not astronomy related. Next Wednesday, Eli is going to be back to give us our Star Wars Fact or Fiction show, so we can take a look at what in the Star Wars universe is completely made up and what could actually be possible with the laws of physics as we know them. And then next Saturday is the next edition of our exploration series, where we're going to take a look at the life and death of stars. So I touched briefly on a little bit about kind of star birth and star death, but if you'd like more detail and kind of more in between of what happens, join us next Saturday for that. All right. Well, I'm not seeing any more questions come in, so I guess I will wrap it up there. Thank you everyone so much for joining me tonight and being patient as I run everything myself. I'm definitely used to having at least Eli here to be my eye on the comments. But we hope that, or I hope that you have a wonderful rest of your evening, and we'll see you next time. Bye, everyone.